today we are going to finish the proof of spectral theorem. Till now we have proved that if T is a normal operator on a Hermitian space V, then W in V is a T invariant subspace if and only if W star is not W star, W perp is T star invariant. We will use this today. So, this we proved in the last class. Okay. That is, if this just means that if TW is contained in W, yeah, it's a subset or subspace of W, then that would imply, and it will be implied by the fact that T star of W perp is a subspace of W perp. Okay. So, this is an if and only if condition. Okay. Now, let us state what we are going to prove from here. Well, let us state in the third board, because in between we need another space. Okay. We require another proposition, that is, well, let us write it down somewhere here, but nevertheless that would be a filler between this and the spectral theorem. So, let us state the spectral theorem first. Okay. Let T be a normal operator on a Hermitian space V. Okay. Then there exists an orthonormal basis of V made up of eigenvectors of T. Okay. That is the spectral theorem. It asserts the existence of an orthonormal eigenbasis. That is all. Okay. And this theorem has lots of applications, from data analysis to image compression or video compression. You will see lots and lots of applications of this. Okay. So, to prove this, we need another proposition, which is this one. If T is a normal operator on Hermitian space V, and V an eigenvector of T with eigenvalue lambda, then V is also an eigenvector of T star with eigenvalue lambda bar, okay, the conjugate of lambda. So we are going to prove this. Okay. Now, once we prove this, this will help us in the induction step in the spectral theorem. Okay. So what we are trying to show, we are given that Tv is equal to lambda v, and to show T star v is equal to lambda bar v. Okay. All right. So first, given this, we would construct a linear operator, normal linear operator on the same vector space, whose eigenvalue is 0 and the corresponding eigenvector is v. How can we construct that? Yes? T minus again? T minus I? Would it work? T minus lambda I, right. T minus lambda I. If you define this with this linear operator S, then at first note that S of, well, at first check that S is a normal operator. Okay. It's obvious that S applied to V is just 0, right? Then S V is Tv minus lambda V, and since Tv is equal to lambda V, you just get that to be 0. So indeed, V is a linear operator, sorry, V is an eigenvector of S such that it has eigenvalue 0. Get the corresponding eigenvalue 0. Now let's consider this S star. If S is a normal operator, it would be equal to what? S star S. They would commute with each other, right? So that means this is T minus lambda I times T star minus lambda bar I, right? The star of this, the bar, how do you define star? You take the conjugate and take the transpose. Okay, so that would give you T star here, and when you take the conjugate, this would be just lambda bar. This is just a diagonal matrix, right? So this one is then equal to T star minus lambda T star minus lambda bar T plus lambda modulus of lambda squared times I, right? Lambda bar I. Okay. And note that T star is equal to T star T, right? So let's go from here to this place. Let's skip this because we are going to use this soon in the proof of the spectral theorem. Okay, so from there we are coming here. We have now S star is equal to T star. We are going to write it as T star T because T was normal. Okay, T star T minus lambda bar T minus lambda T star plus, you can write it as lambda norm squared or lambda bar I, as T star is equal to T star T, since T is normal. Okay. Now this one you can again club together. Okay. So you can write that this is T star minus lambda bar I. You have taken T out from here, and then this times T minus lambda I, right? This is going to give you the same thing, isn't it? You are getting here lambda T star and lambda bar T, okay. And then this one is just this. So that is S star S, all right. So S is a normal operator. Okay. Now what we are going to do, Tv equal to lambda V. From here we wanted to show that T star V is equal to lambda bar V. That means you are given SV is equal to 0, and you are trying to show A star V is also 0. Okay. To show now, well, now it's given that, so we are given SV is equal to 0, and we must show that A star V is also equal to 0, and that will establish the claim, right? How do we show that? Well, A star V comma S star V, if we could show that this is equal to 0, that would mean that A star V is equal to 0, because this is a positive definite form, right? Now what do we know? A star V is equal to, use the last proposition that we proved in the previous class. What was the assertion for Hermitian, not Hermitian, normal operators? SV, right? SV, okay. And what is SV? 0. So this is just 0, right? And that implies that A star V is equal to 0, because the inner product of this with itself is giving you 0, but it was a positive definite inner product, positive definite form, right? By definition, inner product is a positive definite form. Orkodeep, yes. Yes, of course. Otherwise, how do you proceed? That was the only place we have used till now that the form is positive definite, and that's where it's necessary. Okay. So this is if and only if A star V is equal to 0, right? So without the help of the form that it is an inner product, we cannot proceed in this place. Okay. So that's it's a necessary thing for, I mean, to use the positive definiteness of the form to show that A star V is 0 here. Thank you. All right. So with this thing and this thing, okay, we will summarize this proposition just below that, because we need both of the boards for proving the theorem. So this was the first proposition. From the last class. For today, call this proposition 1, and then proposition 2 is that we just proved is that if, well, T is a normal operator, um, for a normal operator T on a Hermitian space V, we have and lambda in C be not equal to 0 if TV is, well, TV is equal to lambda V if and only if T star V is equal to lambda bar V. Okay. So, we will use both these facts in the proof. I would like to wipe this board clear. So, if you are still writing, please let me know, otherwise I will just wipe this out, this one. Thank you. Now, proof of the spectral theorem. Okay. This part also done. Okay, you are still writing, or is it fine to also wipe this out? Thank you. Okay. So, how should we proceed for proving the spectral theorem? By induction on dimension. Okay. And we will see that except these two theorems, I mean these two propositions, the rest of the proof is quite familiar to you. Whatever we are doing, we have done that earlier. Okay. So, for dimension of V equal to 1, what we have? We are asking for an orthonormal eigenbasis, right? Well, T is some linear operator on that. It has an eigenvector, and I mean it has an eigenvector because why does T always have an eigenvector? Yes, but is that necessary? The dimension is 1. So, T is an operator on a complex vector space. Isn't that fundamental theorem of algebra, right? So, its characteristic polynomial will have at least one root. Okay. Now, in particular, we in the case when dimension V is equal to 1, take any eigenvector of T, normalize that. Okay. That is, make its length 1. Then you are done, because that's an orthonormal eigenbasis of the vector space. Okay. So, for dimension V equal to 1, that claim is trivial. Okay. Okay. Now, let us assume that the claim holds for all M in for all m for all integers m for well, we do not require it for all integers less than equal to some certain number. We just require it for just one integer m. So for an integer larger than equal to 1. Okay. And then we try to prove this for dimension m plus 1. Now consider I will consider a Hermitian space V with dimension V equal to m plus 1. Okay. So we'll get down one dimension and we'll have a normal operator on a Hermitian space V of dimension m, and then we can use the induction hypothesis on that. Okay. All right, how do we start? We take T and consider an eigenvector of that. We know that it's a complex vector space, so an eigenvector exists, right? So let V be an eigenvector of T. Okay. Then we use, okay, wait a minute, eigenvector of T. Do we require this lambda explicitly? No, nowhere else. We just require that V is also an eigenvector of T star. Okay. So if V is an eigenvector of T, then V is also an eigenvector of T star, right? Let W be the span of V. Okay. Then we see that W is T star invariant, right? Then W is T star invariant, and that would imply what? So now we are having T star of W is in W. Let's write it down in that language. Then T star of W is a subspace of W. Actually, T star of W is you do not know whether the eigenvalue is 0 or not, so you're not supposed to write equal there, but at least you know that T star of W is a subspace of W. What can you conclude from here? Right, because T is, T star star would be just T, right? So T of W parp is a subspace of W parp. Okay, that is W parp is T invariant. What is the dimension of W parp? Well, we had dimension m plus 1, m, right? And you are having a normal on, well, this is also Hermitian space, right? The form is also symmetric and positive definite on W parp, right? So you are having a normal operator on a Hermitian space W parp, and immediately you can conclude what? That the spectral theorem holds there. Okay. Yes, there exists an orthonormal eigenbasis. Okay. So then T defines normal operator on the Hermitian space W parp. Shivam, are you with the argument till now? Okay. And W parp has dimension 1 less, and you would already assume that it holds for dimension m. Okay. Then we have, well, it should not be, then we just observe this, that dimension of W parp is m. And so by induction hypothesis, there exists an orthonormal eigenbasis of T, call it say V2 dot Vn of W parp, right? So if you call this initial vector, I mean, if you normalize this initial eigenvector to have length 1, then you can just adjoin it with that. Okay. So let V1 be defined as V by norm V. I mean, not V by norm V, 1 by norm V multiplied with V. V is a vector. Okay. And then B is V equal to V1 comma V2 dot Vn is an, well, now we do not require these propositions anymore because we have used both. Then this is an this is what? It's an eigenbasis, an orthonormal eigenbasis of T. I mean, well, it's an orthonormal basis of V made up of the eigenvectors of T. Orthonormal basis of, we have clubbed, I mean, we have just adjoined a basis of W with W parp, right? And we saw that if two spaces are independent, then clubbing their bases together makes a basis for their direct sums. Okay. So this is an orthonormal basis of W direct sum W parp, right? But what is W direct sum W parp? It's V, right? Because the form is, well, it's an inner product. It's non-degenerate on W in particular. So V decomposes as W direct sum W parp. Okay. And so this is the basis that we talked about. Okay. That finishes the proof of the spectral theorem. Okay. Now we'll draw a few corollaries from this. Okay. So can you tell and interpret the spectral theorem in terms of the Gram matrix? Well, not the Gram matrix, excuse me. In terms of, so can you interpret the spectral theorem in terms of the matrix of the linear transformation T? Yes, yes. Because an eigenbasis exists, it should be diagonalizable. The operator should be diagonalizable. So there exists some, I mean, with respect to that eigenbasis, the matrix representation of T would be diagonal. And what more? The eigenvalues would be on the diagonal, right? And what can you tell more about the matrix of the change of basis? Well, if you go from one basis to another, when the form is defined, I mean, we are just saying that with respect to some basis, I mean, so what we are doing here, we are saying that there exists an orthonormal basis. So maybe we are not given that basis at the beginning, but we will be able to construct such an orthonormal basis. Okay. So yeah, I mean, what we are trying to say is that the spectral theorem guarantees that there exists an orthonormal basis of V made up of the eigenvectors of T. So in particular, T is diagonalizable. That means you will always have an eigen basis of T, but that may not be what you call an orthonormal basis of V yet. Okay. So what you have to apply then? The Gram-Schmidt process. Does the Gram-Schmidt process make this invariant? I mean, make the eigenspaces invariant. So this is something to ponder yet. Okay. I mean, how given a basis you come up with an orthonormal eigenbasis. So we know that it exists. Okay. But how do we come up with that? Okay. Well, we just do the steps that we have done here. Okay. So we start with some basis, some eigenvector, we normalize it, okay, and we see the rest of the things. Okay. I mean, we are now in W-perp. Again, in W-perp, we consider an eigenvector of T and normalize that, and we go on. Okay. Okay. So it's just a proof, but the proof is algorithmic. All right. So in terms of the matrix of T, let's see what we have. So the first corollary. By the way, normal operators are defined in terms of an orthonormal basis of V, right? Because we define T star in terms of an orthonormal basis. So the first question to you is that if we shift from an orthonormal basis to another orthonormal basis, what can you tell about the matrix of the change of basis? Right. And so P star, both are orthonormal basis. You see, you are going from an orthonormal basis to another orthonormal basis. So the Gram matrix is identity, and in the new basis, our Gram matrix is also identity. And so, what is about the matrix? What? No, not P star equal to P. That would be Hermitian, but it should be a unitary matrix because P star P would be identity. Earlier you had P star AP. Yeah. So earlier you had, yeah, P star should be equal to P inverse. That's right. So P star AP was the new Gram matrix A dash, and now since both of the bases are orthonormal, you have an identity here and an identity here. Okay. So basically, you are having P star P is equal to identity. That is, P star P is an unitary matrix. Okay. So here, what it will mean that given a normal operator, the matrix representation of that operator is such that there exists some unitary matrix P such that P star AP. Now A is the matrix of the matrix of representation of this, what you call the of T. Okay, and this is going to give you a diagonal matrix T with all the elements on the diagonal, I mean all the things sitting on the diagonal being its eigenvector, eigenvalues. Okay. Let's see this clearly. So at first, let me write down the corollary. let A in M N C be a normal matrix. Then there exists an unitary matrix P such that P star A P is equal to is diagonal. Okay. And why we are writing here P star A P? Because it's a unitary matrix. So P star is just P inverse. This is P inverse A P is diagonal, since P is unitary, because we are at most changing from an orthonormal basis to another orthonormal basis. Kaushik, any doubts, any questions? Please ask me. You seem a bit lost. Where exactly? The eigenvectors. At first, you have to find out the eigenvalues, right? So, how do you figure out the eigenvalues of a linear operator? Characteristic polynomial. So, it's a degree n polynomial, right? Now, since your field is complex, that means you have a polynomial with complex coefficients. It has a root. C is algebraically closed. So, every polynomial has a root. That is the fundamental theorem of algebra, right? That means an eigenvalue exists of t, and once an because it's a root of the characteristic polynomial, right? And then once you have a root of the characteristic polynomial, then that means that there exists. So that is an eigenvalue. So that will imply that there exists an eigenvector. Well, what it means to have an eigenvalue? Let's recall. So T is a linear operator, okay? And suppose with respect to some basis B, its matrix is A, and you just said that A has an eigenvalue, some eigenvalue lambda. Okay? So consider A minus lambda I, okay? And then the characteristic polynomial was, this satisfies the characteristic polynomial. So in other words, the determinant of this is 0, right? This is in particular a non-singular matrix. Okay. Now, what do you know about non-singular matrices? So, if A is a non-singular matrix, then what do you know about the solution of this equation? There would be a non-trivial solution. That is your eigenvector. Okay. So, there will always be an eigenvector if you have a solution to this equation. Okay. If there exists a solution to this equation, that means there exists some lambda for which you are having this equal to 0. That means this matrix is singular. That means there exists some non-zero vector x such that A minus lambda I times x is equal to 0. This x is coordinates of your eigenvector with respect to the basis for which A is the matrix of representation of this linear operator T. Yeah, so that was your first doubt. The next one. So from here to here, right? From the spectral theorem to the corollary. Okay, let's see. So let's take the theorem and get to the corollary. T is the linear operator, a normal operator from V to V, and V is at first some basis. Do not take this to be this basis, maybe call that basis something else, call it D. D, a basis of V, and let A be the matrix of T with respect to the basis D of V. Okay. Then what the theorem asserts, that there exists an orthonormal eigenbasis. Okay, an orthonormal basis of V which is made up of the eigenvectors of T. Okay. Now, with respect to B, the matrix A dash of the matrix of T, how it should look like? No, at first, if it is an eigenbasis, then how should be the matrix of representation of T? Diagonal matrix. The matrix of T, that is a diagonal matrix with, yes, eigenvalues sitting on the diagonal. Okay, sitting on its diagonal. All right. Well, and also, I mean, since we talked about a normal operator, it was not just any basis of V. We already started with an orthonormal basis of V. And that existed since V was a Hermitian space. Okay. So now, how does the matrix of a linear operator changes under change of basis? Yes, P inverse, right? P inverse AP, and that is equal to A dash. Okay, but we know something more about P. I mean, this matrix P. It's an unitary matrix, right? Because we were changing from an orthonormal basis to another orthonormal basis. Okay. So that is if and only if P star AP is equal to A dash, since P is unitary. Okay. Right. If you come the other way, you will end up with this one. But then this P star is equal to P inverse. So either way, you will end up with this equation, that is, it is P star AP equal to A dash or P inverse AP equal to A dash, where P is an unitary matrix. Okay. So in particular, now if you specialize this operator to a Hermitian operator or an unitary operator, you will get the same conclusion, right? Because a Hermitian operator or a unitary operator or an unitary operator are just special cases of normal operators. Okay, and do you recall the eigenvalues of a Hermitian operator? They're real. Okay, so in particular, if you were given a Hermitian matrix, there exists some matrix P such that P inverse AP is equal to a real diagonal matrix. Okay, if your original matrix is Hermitian. So this is corollary 1, and this should be corollary 2 for Hermitian matrix A. There exists unitary matrix P such that P star AP is real, well, it is a diagonal matrix with real entries. Real entries means real entries on the diagonal. 0 is of course real. Okay. So yeah, that's all for today's class, and in the afternoon we will introduce the functionals and dual spaces. Just one class on that, and that would be the last class.